Hello, we're glad you've joined us for this live webinar, Applications of Counterflow Centrifugal Elutriation, Revival of an Old Tool. I am Judy O'Rourke of LabRoots, and I'll be moderating this session. Today's educational web seminar is presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. It's brought to you by Beckman Coulter Life Sciences. Beckman Coulter Life Sciences develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. More than 275,000 Beckman Coulter systems operate in both diagnostics and life sciences laboratories on 7 continents. For over 75 years, our products have been making a difference in people's lives by improving the productivity of medical professionals and scientists, supplying critical information for improving patient health, and delivering trusted solutions for research and discovery. To learn more about Beckman Coulter Life Sciences, please visit www.beckman.com. So let's get started. You can pose questions to the speaker during the presentation while they're fresh in your mind. To do so, simply type them into the Q&A box, which will open when you click the green Q&A button at the lower left of the presentation window. Questions will be answered after the presentation. To enlarge the slide window, click on the screen icon in the lower right-hand corner of the slide window. If you experience technical problems seeing or hearing the presentation, just click on the support button found at the top right of the presentation window, or report your problem by clicking on the green Q&A button at lower left. I now present today's speaker, Anisha Rathi, PhD, a postdoctoral research associate in cell and molecular biology at St. Jude Children's Research Hospital. After completing a master's degree in virology, Dr. Rathi joined Professor Timothy Chambers at the University of Arkansas for Medical Sciences in 2011 for her graduate studies. She earned a PhD in biochemistry and molecular biology with her work studying mechanisms of cell death induced by microtubule inhibitors in primary acute lymphoblastic leukemia cells, ALL. In collaboration with Dr. Walter Hittleman at the MD Anderson Cancer Center, Dr. Rathi learned about the technique of centrifugal elutriation using Beckman's JE6 elutriator rotor. In 2016, she began postdoctoral work in Joseph T. Opferman's laboratory at St. Jude Children's Research Hospital, working on development of anti-cancer strategies in hematological and solid tumors. Her current research focuses on targeting anti-apoptotic BCL2 family proteins as a strategy to improve survival in ALL and neuroblastoma. Dr. Rathi will now begin her presentation.
Thank you, Judy, for that introduction. Hello, everyone. Thank you very much for attending this talk. As Judy mentioned, I'm Anisha Rathi. I'm a postdoc in Dr. Opferman's lab at St. Jude, and I'll be giving a talk titled Applications of Counterflow Centrifugal Elutriation, abbreviated as CCE, as a revival of an old tool, and I'll explain why I'm calling it a revival in the next slide. So before I proceed, I wanted to clarify the difference between elutriation and centrifugal elutriation. So elutriation is just a technique to separate small particles suspended in a fluidized bed into different size groups by passing an increasing flow rate through the elutriation chamber. In elutriation, particles are suspended in a moving fluid, which can be liquid or gas. However, in case of centrifugal elutriation, it's very similar to elutriation, except that the fluid is pumped into a rotating separation chamber that converges into an outlet tube, and we'll see the details in the coming slide. So before I go into the technical details of elutriation, I would like to shed some light on the history of the technique of centrifugal elutriation. This technique dates back to 1948, when the first apparatus that exploited differences in velocity sedimentation for the separation of cells by counterstreaming centrifugation was described by Blundell. The Beckman Instrument Company later modified this instrument and named it Elutriator and termed the process centrifugal elutriation. And if you would look up on PubMed, you would notice that majority of the reported publications using this technique, almost 90%, were until 2000 or even before that. So after that, the use of this technique has dropped drastically, and missing technical skill necessary for the assembling and operation of this instrument is partly to blame for reduction in uses of CCE, or counterflow centrifugal elutriation. However, several areas of scientific research can still benefit tremendously from this tool, and therefore this tool is in need of revival. So we'll first talk about the principle of CCE, or counterflow centrifugal elutriation. CCE can separate cells which differ in cell sizes, which is the basic principle of CCE. The way this works is that the cells are introduced into a chamber and they are under the influence of two opposing forces. One is the centrifugal force and the other one is the fluid velocity, or counterflow. The centrifugal force drives the cells away from the axis of rotation, whereas the fluid velocity drives the cells towards the axis of rotation. Therefore, these two forces act in opposite directions. And the cells attain an equilibrium based on these two forces inside the chamber. Cells in the elutriation chamber, they reach the equilibrium position where these forces are equal. The key factors dictating the equilibrium position are the cell diameter and density. So as I mentioned, the two forces that act upon cells in the chamber. So in this figure, you can see that in the first A section, the cells or sample is suspended in a buffer and they enter the chamber. Then the sedimentation tendency of particles is balanced by counterflow and they attain an equilibrium depending on the cell sizes. And then the flow, if we increase the flow or counterflow, we can cause the sedimenting particles to elutriate from the chamber. And the smallest cells, which are near the exit, will therefore elutriate or come out first, followed by the larger cells. And hence, by collecting different fractions of cells with subsequent increases in counterflow rate, we can separate cells of different cell sizes. This technique needs a lot of optimization. For example, if you start to use this technique on a new cell type, you have to optimize a lot of conditions before you proceed. The process of elutriation requires optimization depending on cell type, elutriation buffer employed, and the specific apparatus used. The basic formula used, which can help you with the optimization, is the Stokes law, according to which FV, or sedimentation velocity, is given by this formula, which you can see on the screen. Here, R is the radius of the particle, rho P is the density of the particle, rho M is the density of the buffer, and eta is the viscosity of the buffer. Thus, sedimentation velocity is proportional to cell diameter and density, and since diameter or the radius is raised to the second power, it contributes more significantly. This diagram shows the basic components of the CCE system. The exact apparatus may vary in one aspect or the other, but as I mentioned, this is the basic components of the CCE system. In this, the stroboscope is placed and fixed at the bottom of the centrifuge. The centrifuge is hosting the rotor that is running with constant speed. The pump is turned on and sterilization takes place by running 70% ethanol through the system, followed by a physiological buffer to remove traces of ethanol. The physiological buffer is then replaced by the elutriation fluid at an initial flow rate. Here you can use 10% bleach instead of 70% ethanol as well. The preliminary run also serves to remove bubbles from the system. And as I will mention ahead, that removal of bubbles is an important critical step of operating this instrument. The loading chamber serves as a sample mixer and in its bypass position traps small remaining bubbles and compensates pump pulsation. The bypass valve helps to remove residual bubbles from the sample mixer chamber. And this is a real instrument, a centrifugal elutriator, which I personally used in my lab during my PhD work. And this on the left-hand side is the front view, and this is the pump by which we use to control the flow rate. And this is the top view. This is the separation chamber. So you can use CCE for different applications. I'll take the example of cell synchronization by CCE to describe the whole technique. We recently reported that primary acute lymphoblastic leukemia, or ALL cells, they undergo death in either G1 phase or in M phase when treated with vincristine and other microtubule targeting agents. And these being primary cells, we were not able to synchronize them using the traditional synchronizing agents such as double thymidine block or different other synchronizing agents. So we started looking for other alternative options for synchronizing them, and that's when I came across the idea of centrifugal elutriation. The ability to separate ALL cells into different cell cycle phases by CCE was instrumental in reaching this conclusion. The rotor we used for our experiments was Beckman JE6 Elutriator rotor. In this webinar, I'll describe the technical details and offer practical tips for the application of CCE to the preparation of primary ALL cells in different cell cycle phases. And these steps remain almost the same for other purposes as well. You just have to optimize it, fine-tune it, depending on your cell type and the factors I mentioned before.
Dr. Rathi, a question has come in about that last slide. I'm hoping to pose it right now.
Sure.
You mentioned about the use of CCE in synchronizing leukemia cells, which are suspension cells. What about adherent cells? Can CCE be used for them as well?
So that's a very good question. The CCE is a very good technique for all the suspension cells like AML, ALL. However, adherent cell types pose potential problems due to their propensity for clumping and possible adherence to the surfaces of the tubing and elutriation chamber, and those should be investigated with caution. I personally would not recommend, but if you can give it a try and if it works with your system, you can go ahead with it. But as I mentioned, for the reasons above, caution is needed.
Thank you.
And moving to the next slide, this is the experimental design to investigate interface cell death in ALL cells. I wanted to know how cells are dying in specific phases of cell cycle when treated with one of the chemotherapeutic drugs called vincristine. So the idea was to isolate or obtain cells in specific phases of the cell cycle, G1 or G2M phase, and then treat them with vincristine and follow the cell death pattern. But as I mentioned, I could not separate the cells in these cell cycle phases using classical synchronizing agents. So I used the technique of centrifugal elutriation, which is based on the principle of cell size differences. And the cells, they increase in size as they proceed through the cell cycle. So cells in G2 or M phase would be larger than the cells in S phase, and they would in turn be larger than the cells in G1 phase. This enlists the protocol steps required for a successful execution of CCE or elutriation. First step is preparation of elutriation buffer and materials. Second, assembly of the elutriation system. Then priming of the elutriation system. followed by preparation of the cell sample, introduction of cell sample into the elutriation system and collection of fractions, followed by flushing of the elutriation system, and finally analysis of fractions and collections of different pools to make sure the CCE worked okay. I will be describing each of these steps in a little bit more detail. So the first step is preparation of elutriation buffer and materials. Elutriation buffer, the one I used was Hank's balanced saline solution, which had phenol red in it, and it was supplemented with 2% fetal bovine serum and 1.6 gram per liter of 2-naphthol 6-8 disulfonic acid dipotassium salt, or NDA. Then I labeled 50 ml conical tubes for collection of fractions, so that there are tubes labeled wash 1 and wash 2, fractions 1 to 20, and the last tube was labeled as stop. So a total of 23 tubes were labeled.
Dr. Rathi, we have a question about this slide as well. What is the role of NDA in the elutriation buffer?
So NDA imparts a negative charge to the cells, as a result of which it prevents cell clumping. So it's an important agent to prevent cell clumping, which is very crucial for successful elutriation run, because I mentioned it's all based on differences in cell sizes. If the cells would clump, the whole cell size difference would be thrown off. You can use any chemical which would do the same thing instead of NDA.
Thank you.
Mm-hmm. The next step is assembly of the elutriation system. This can be a little bit tricky just based on reading this. However, if you buy the instrument from a specific place, those people can also help you with the assembly. So basically what you do is first the strobe assembly should be installed into the Avanti J26X XPI centrifuge, which is the one we used, so that the power cord is fed out of the chamber to the port on the left side. The strobe flash lamp, which is on top of the centrifuge, should be at the front of the chamber so that it will line up with the viewing window when the centrifuge is closed. This will allow you to look at the cells roughly when the cells are under the process of elutriation. Next, the JE 5.0 rotor should be set straight down onto the centrifuge drive hub and secured with a T-handle hex wrench. Once the rotor is secure, the quick release assembly containing the elutriation chamber, counterbalance, rotating seal assembly, and a mounting plate can be placed into the rotor. It can sound a little complicated, but it's very simple to do. Once everything is in front of you, anyone can do the assembly. Then next, the flow system should be assembled using a variable speed pump. As I showed in the previous figure, on the left-hand side, we had a pump and tubing to pump buffer into the elutriation chamber and collect buffer as it flows out of the elutriation chamber. Lastly, turn the centrifuge on and set the specifications necessary for the experiment, such as name of the rotor, temperature, duration of run, acceleration, and speed. The pump here is used to set your flow rate. So remember how I mentioned two opposing forces, centrifugal force and the pump flow rate. So the pump is used to monitor the flow rate, whereas the centrifuge speed will monitor your centrifugal flow rate. You can keep one of these as constant and change the other one to elute yourself. Next, the system should be flushed with autoclaved water. So this is the priming of the elutriation system. First, so before we introduce cells into the system, we have to first prime the system. For that, we use 5% bleach, or you can use 10% bleach, to flow through or to release bubbles and back pressure. This also sterilizes the whole system. Stop the centrifuge and inspect the chamber for any leaks. Then next the system should be flushed with autoclaved water. introduce the elutriation buffer and allow it to flow through the system to flush out the water and then recycle the buffer through the system. So finally, the viewing window needs to be adjusted so that the elutriation chamber can be seen at the current speed. And the reason you want to use...
We have another question from the audience. It just popped up. Why do you run autoclaved water after running bleach through the elutriation system?
Sure. So bleach can lead to formation of precipitates from the elutriation buffer, which may lead to clumping of the cells, and it can also cause harm to the cells. That's the reason you have to flush out all the leftover bleach from the system using autoclaved water. And then only we introduce the elutriation buffer into the system.
That is great. Thank you.
Mm-hmm. Now we have come to preparation of the cell sample. We count cells and obtain around 300 to 400 million cells in 50 ml conical tubes. Please note that these are ALL primary cell cultures. The cell number may vary depending on the cell type you are working with and your requirement. Pin down the cells at 1210 G for 3 minutes, aspirate off growth media, and resuspend cells in 25 ml of elutriation buffer by pipetting up and down gently. You have to make sure every step is very gentle because you don't want to damage the cells. In order to reduce cell clumping, it is essential to pass cells twice through a 25 gauge needle. This will make sure the cells are not clumped. You can further take a look at the cells under microscope to make sure the cells look independent of each other and are not clumped. And after that, now it's time to introduce the cells into the elutriation system and then collect the fractions. For this, the cell samples are introduced into the system by pouring the cells into the reservoir tank, which has the elutriation buffer recycling through the system. The progress of the cells entering the system can be tracked via the viewing window, which is on top of the centrifuge. So you can see the cells entering the chamber even when the centrifuge is closed and running. Then once you are comfortable that the cells have entered and are retained in the chamber, you can start collecting fractions, and you can change the speed, or as I mentioned, you can either keep the speed constant or the flow rate constant and change the other parameter. In this case, I changed the speed, and with subsequent changes in speed, I collected fractions. I collected fractions of 50 ml each, and once all fractions were collected, so the first 2 fractions were my wash 1 and wash 2. That's when the smallest debris particles come out of the chamber, followed by 20 fractions of the cells. And then I stopped centrifuge and collected the last fraction and called it stop fraction, which usually has cell aggregates. Finally, you have to clean up the system so that it's ready to use for the next time you want to use it. For that, after the centrifuge has stopped, completely flush the system with autoclaved water, followed by 10% bleach. You can also use 70% ethanol. Turn off the pump, remove the input and output hose from the quick release assembly, and pull out the pin from the anchoring table. If this centrifuge you are using only for elutriation purposes, you can leave the assembly in the centrifuge itself. However, more economical would be to use the centrifuge for other non-elutriation purposes as well. So in that case, you have to take out the whole assembly every time after use and reassemble it every time you need to use it. Now it's time to know whether the elutriation you just carried out worked or not. For that, you need to analyze the fractions and collect the pools. So to begin with, I spun each fraction at 2000 G for 5 minutes at 4 degrees Celsius and aspirate off elutriation buffer. For the G1 phase pool, I resuspended fractions collected in the speed range of 788 G to 661 G. They were fractions 1 to 5 in 1 ml PBS. For the G2M phase, I resuspended fractions collected in the speed range of 387 G and 333 G, which were fractions 17 to 20. Now, the fractions you pool can be optimized. So initially, before pooling the fractions, I had already done cell cycle analysis on each of these fractions. So I knew that pooling fractions 17 to 20 is giving me good amount of G2M phase cells. So you can do that on your own individual set of experiments, and then you can find out pooling which fractions will give you a good pure population of that specific phase of cell cycle. And then I spun down the cells as above, resuspended in 10 ml of growth media, and take a cell count. The cell cytometer we used to take the cell count also gave us cell viability and cell diameter. So we knew that the diameter of later fractions were more than the diameter of the earlier fractions, which is a very early indication that the elutriation went well. And the good percent viability also indicates that the process did not have a detrimental effect on the cells. But for ensuring that the elutriation went well, we have to take an ELICOT from each pool to be analyzed for DNA content via propylium iodide staining and flow cytometric analysis. This will tell the cell cycle phase each pool fraction belongs to. The remainder of each pool can then be used for further experiments. This is representative results of one of the elutriation runs we carried out. As you can see on the top left corner, the cell diameter is given on the y-axis and the fraction number is given on the x-axis, the fractions 1 to 20. And you can see that the cell diameter is increasing with each increasing number of fractions. So the fractions collected first, earlier, they had smaller cell diameter as against the fractions collected later in the elutriation process, which had higher diameter. So as I said, this is an early indication that everything went well. Then this is the cell cycle analysis of control cells prior to elutriation. And they have a good proportion of G1 phase cells, S phase cells, and G2 or M phase cells, as shown by the DNA content by propylium iodide staining. Now these are the pooled fractions from the elutriation. The one on the left is early fractions, which are fractions 5 to 8. They had all the early G1 phase cells. And you can see the content of G1 S phase cells is 95.4% as against 71% in prior to elutriation. So we had been able to get a pure population of early G1 phase cells after elutriation by pooling fractions 5 to 8. Similarly, the intermediate fractions, which are obtained by pooling fractions 13 to 16, had a pure population of late G1 and S phase cells. And finally, the late fractions, fraction 19 to 20, they had a very good population of SG2 and M phase, but mostly foreign DNA content. And we further verified this result by immunoblot analysis for different cell cycle phase markers, and that further confirmed these findings. Then we used these pure cell cycle phase cells to carry out our experiments to find out the cell death pattern induced by vincristine in these ALL cells. So I'm not going to go into details of those experiments because we are talking about just the process of elutriation. You can anytime go back to my paper and look for the details. But talking more about the process of elutriation, there are some steps during the process which are very critical and challenging. Caution has to be taken to make sure that those are catered. For example, it's important to ensure that the cells are monodispersed and not clumped at the start of the run. Then optimization of the conditions of counterflow rate and rotor speed is very important. So before you start any elutriation, you have to run the elutriation few times. You can start with the Stokes law to calculate what counterflow rate would suit your conditions. Like for me, when I did elutriation, maximum time I spent was in optimizing the whole thing. Once everything was optimized, it was easier from there on. Then it's important to ensure the components of the system are clean and free of debris. And finally, avoid introduction of air bubbles into the flow lines. So you have to, the tubing usually is transparent, so you can see if there are any air bubbles in the tubing. And if there are, you have to make sure you remove them before you introduce yourself into the system. This technique has a lot of advantages, but I have listed the most important advantages here. The cells are not subjected to harsh conditions of chemical treatment or nutritional deprivation, which are usually used to synchronize the cells. And it can be recovered in excellent yield, essentially unperturbed. This contrasts with cells synchronized by chemical means, which may harbor drug-induced damage. For example, a recent study using NB4 cells derived from acute myeloid leukemia blasts directly compared centrifugal elutriation and other methods, including arrest with serum starvation, hydroxyurea, or treatment with a cyclin-dependent kinase 1 inhibitor, RO3306. And it was found that elutriated cells and cells arrested at comparable phases appeared similar with respect to DNA content and cyclin expression. However, when the proteome was examined, major changes in protein abundance, particularly stress-related and arrest-specific proteins, were observed in the arrested cells and not in the elutriated cells at equivalent cell cycle positions. So these results clearly highlight the utility of CCE for the production of unperturbed cells and emphasize that caution should be used when interpreting data from cells synchronized by other means. This method is still regarded as one of the best ways to prepare unperturbed synchronous yeast cultures for cell cycle studies and even mammalian cultures. And finally, the cells obtained by this method can be cultured for many days without any signs of distress, which we confirmed. We took the cells and monitored the viability for a few days after the elutriation was performed, and the cells were doing fine. However, no technique is without any limitations. So there are some limitations to this technique as well. For example, the most important is that it works best with cells that significantly increase in cell size as they advance through the cell cycle. So some cells, for example, such as early embryonic cells, the cells progressively decrease in size as they divide. So this technique will not be applicable to those cells. However, those type of cells are very rare, so it should be applicable to majority of the cells. The cost of the specialized centrifuge, rotor, and accessories can be very high. However, you can collaborate with some labs which already have the system with them, and that way you can work on the cost factor as well. Then scheduling inconveniences. So elutriation runs typically take 5 to 6 hours, followed by time needed if the cells obtained are subsequently needed for other experiments. So this can create some scheduling inconveniences if other people are also requiring the instrument. You have to plan everything in advance and reserve the instrument in advance. if you plan to run the elutriation that day. And finally, this method works best on cells with round or oval shape. This method has lots of applications.
Dr. Rathi, can I stop you 1 second? Another question has just come in. How do you find out the cells are increasing in size as they advance through the cell cycle?
So, yes, so for a given population of cells in suspension, this can be established initially and easily by examining the relationship between DNA content and site scatter. Site scatter is dependent on cell size. So both parameters can be measured simultaneously by flow cytometry after rubidium iodide staining. And a linear relationship between site scatter and DNA content provides confidence that cell size increases with cell cycle advance, and thus the CCE has the potential to separate cells based on cell cycle phase. If you do not get the linear relation, then it's a matter of concern.
Okay, thank you so much for that.
Then talking about the application, the most important and widespread application of centrifugal elutriation so far has been unperturbed synchronization of animal cells and yeast cultures. Also, although CCE is readily amenable to suspension cell cultures, it can also be applied to subcellular fractions. For example, nuclei from murine pre-B cells have been successfully site separated using this technique. Centrifugal elutriation has also been reported to separate hematopoietic cells, mouse tumor cells, testicular cells, and a variety of other specialized cells from other cells. And interestingly, recent advances are expanding uses to the separation of cells from healthy versus cancerous tissue and to the production of specific cell types for immunotherapy, because you can enrich for cells within a population of immune cells because of difference in cell sizes using this technique. With that, I'll conclude the talk. This picture on the top left is a phoenix, which revives itself. So I thought it was perfect for this presentation because centrifugal elutriation it needs a revival because of all the advantages it has. There lies a huge untapped potential of CCE in making significant contribution to wide areas of scientific research, and this old tool is therefore worth reviving in current times. The ability to prepare cells enriched in specific cell cycle phases by CCE has greatly facilitated cell cycle research in both yeast as well as mammalian cultures. A successful method for obtaining primary ALL cells in different phases of cell cycle using CCE was just described, and similar principle of operation applies to other cell types. With that, I would like to thank you everyone for your attention, and I'll be happy to take any questions. Thank you.
Thank you, Dr. Rathi, for your presentation. We addressed some questions during the presentation, so if we weren't able to address your question, we will follow up afterward. I would like to once again thank Dr. Rathi for her presentation. Do you have any final comments?
I would like to thank everyone, all the audience, for patiently listening to the talk. And if you have any more questions, even after the webinar gets over, feel free to email me. I would be more than happy to help you. This technique definitely needs some guidance to learn, and I'll be happy if you have any questions. For me, Dr. Hittleman from MD Anderson Cancer Center, he was an expert at this technique, and I was fortunate to learn it from him. So I hope you find some guidance and you are able to harness all the benefits this technique has to offer. Thank you.
Well, thank you again, Dr. Rathi, and I'd also like to thank the audience for joining us today and for their interesting questions. We would like to thank our sponsor, Beckman Coulter Life Sciences, for underwriting today's educational webcast. This webcast can be viewed on demand through February 17, 2018. LabRoots will alert you via email when it's available for replay, and we encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.